Morning, everyone. So we are going to get started. We'll finish up chapter 3 today and then hop into chapter 4. Make note that your first test will be conducted on this Sunday through Monday. It'll pop up under tests in Moodle, okay? So Sunday at, like 5 a.m. if you want to take it, you can. Otherwise, you have Sunday through Monday, because I know some people work on the weekends. It is timed. You'll have like an hour and 15 minutes for it. So once you get started, you just roll through it. Okay. Let's my tablet. Give me just a second. I'm just getting those lectures together. All right. Great. So we don't want to do chapter 4 yet. Let's hop over to chapter 3. Okay. So we finished up real quickly. We were talking about specific heat. So we've got heat capacity, which is the quantity of heat, and it's usually represented in joules, required to change the temperature of a given amount. So we know the amount of the material by 1 degree Celsius, but we are going to be doing more work with specific heat capacity, which is showing us the amount of energy it takes to raise 1 gram of that material 1 degree Celsius. So that would be the specific heats value. So here's a list of specific heats. These are consistent with whatever the material is. So if I'm dealing with lead, it always has this specific heat. What you'll notice is that water actually has the highest specific heat capacity on the chart, which is kind of weird because you would think, oh, like we need more energy to melt a metal. Now metals do have higher boiling points and melting points, but if I had 1 gram of gold and I had 1 gram of water and they were both at 25 degrees Celsius and I wanted to raise both those things to 26 degrees Celsius, it takes more energy to raise the water that 1 degree. And so this is sort of the reason that, like, desalinization again is not the answer to our water shortage problems, because it requires so much energy to change the temperature of water. If anyone's ever lived at the coast, this is a reason why it's cooler in summer and warmer in winter when you get close to the water, because the water acts as sort of an insulating buffer. So it takes a lot of energy to heat it up, and it has to release a lot of energy to cool back down. So the equation, Q equals MCAT, Q equals M times C times delta T, or your heat which is a measure of the transfer of energy in joules, is going to be equal to your mass times your specific heat capacity times your temperature change, delta T, okay? Now that little delta symbol or that little triangle, that means change in temperature. That means your final temperature minus your initial temperature. So if you're going up in temperature, this number will be positive. If you're going down in temperature, this number will be negative, which Q can be positive or negative. If Q is positive, you're dealing with an endothermic reaction. If it's negative, you're dealing with an exothermic reaction. Now, I'm going to go back to that previous page just to look at the units for specific heat capacity. Joules per gram degree Celsius. So the joule is above this fraction bar. The gram and degree Celsius are below the fraction bar. So three units in this derived unit, all right? If this value is in joule per gram degree Celsius, the other things have to match those units, all right? So joules for Q, mass has to be in grams, Celsius is in, or I'm sorry, specific heat is in that joule per gram degree Celsius, and then temperature needs to be in Celsius, okay? Some people will say, oh, well, can I change my specific heat to match like kilogram and Fahrenheit? Don't do that. That would drive you crazy, okay? Match the other units to get to these units. So let's look at a problem. Well, and first of all, you're not going to be doing dimensional analysis with heat capacity problems. So the conversion factor thing, we're not going to be doing with this because this is just an equation. You have 4 variables. Well, technically 5 because this is a change in temperature. You will be given 3 of the 4 or 4 of the 5, and you solve for the other one. So let's look at this problem here. Gallium is a solid at 25.0 degrees Celsius, and it melts at 29.9 degrees Celsius. If you hold gallium in your hand, it can melt from your body heat, okay? So this change in temperature can happen from your hand. How much heat must 2.5 grams of gallium absorb from your hand to raise its temperature from 25 to 29.9? And it says, hey, the specific heat is this thing right here. So anytime in this next test, if they're talking about specific heat capacity, just write out the equation Q equals MCAT. That's a good place to start. So Q equals MC delta T. In this case, let's figure out what our given information is. So we're given the mass, right? So we know that we have mass is equal to 2.5 grams. We actually are also given the specific heat, right? It's down here. So we have a specific heat of 0.372 joules per gram degree Celsius. And then the change in temperature is your final temperature minus your initial temperature, okay? So delta T is equal to T final minus T initial. In this case, it's equal to 29.9 minus 25.0. So we end up with what, 24? Nope. We end up with 4.9 degrees Celsius. So again, I think the toughest thing is going from this to this. But if you write it all out, then it's actually really easy, right? We're just going to plug it into our equation. So we know Q is equal to my mass, 2.5 grams, times this specific heat, 0.372 joules per gram degree Celsius, times my change in temperature, 4.9 degrees Celsius. And I like to put my units in because, again, I can see things start to cancel. Celsius cancels with Celsius. Grams cancels with grams. And the only unit we're left with is a joule. So plugging that in. I got 4 point, let's see, 2 sig figs here, so 4.6 joules. Okay, not too bad, right? As long as you lay it out correctly. So let's do a couple more. Let me clear this out. I'm not sure if they have one in the slides, so let's take a peek, and if not, I'll pull something else up. Okay, so it tells you how to do it. Great. Okay, yeah, that's the end of those slides. So we're going to do a couple more of these. So again, there's always additional worksheets and stuff in Moodle. If you're ever like wanting to go look around for additional help, I put stuff in there. Okay. Oh yeah, the triangle. Okay, let me show you guys the triangle here. So we're gonna work on the first two. So here is a way to, I guess, help you isolate variables, because some people have trouble with isolating variables. So you can put a Q up on top, M, C, delta, T. This is a division bar. These are multiplier bars, okay? So if I want to solve for Q, Q will equal this times this times this. If I want to solve for mass, my value will equal Q divided by C times delta T. If I want to solve for delta T will equal Q divided by mass times C. So just a fast way to isolate variables. Okay, I want you to do number 1 and number 2 here. You guys have, I'm gonna give you 6 minutes. I'll give you till 8:20 to work through those. While you're working on them, if you have any questions, ask me. I'll help you out. So for this first guy, given information, I know my mass because it says right off the bat, it's 15.75 grams. And it says it absorbs this many joules. Okay, so this is one place where I see students get confused is they mix up Q and C. So Q is talking about heat. Your unit will be joule or calorie. It's a simple unit. C is the funky unit. That's the specific heat, right? So in this case, we are given Q. Q here equals 108.6.75 joules. Temperature change 175, delta T is 175 minus 25, so 150 degrees Celsius. And I'm actually going to put a little dot there because it's 3 sig figs. Calculate the specific heat. So we want to solve for C. So C equals Q divided by my mass times my change in temperature. You just plug it in. So 108.6.75 joules all over the 15.75 grams times the 150 degrees C. You'll notice none of the units cancel. That's good because specific heat is those funky units. So what do we got? So this whole thing, I gotta write it out, sorry. 108.6.75 joules divided by 2.3625. Okay, so we should get C is equal to 0.46. And the units on this thing are going to be joules per gram degree Celsius. I don't know why this pen isn't working now. Gram. Not liking me right now. My sound is getting messed up. Yeah, it seems like it's a little choppy. Usually it lets me know. Okay. Okay, well, it's joules per gram degree Celsius. You guys are still having trouble hearing me. Let me know if it's still choppy. So second guy here, how many joules are, it's still messed up. Okay, hold on 1 second. I'm trying to unshare and reshare my screen. Sounds like I'm underwater.